Good morning, everyone, and welcome to this week's Colloquium, Electrical Engineering Colloquium. This is a very special colloquium which happens once a year, which is the annual Akira Ishimaru honorary lecture. And we'd like to thank our donors who are colleagues and ex-students of Professor Ishimaru who made this possible. Our today's speaker actually has, in some sense, the same vein as Professor Ishimaru. As many of you know, Professor Ishimaru is known for a long history of deep and insightful projects in electromagnetics and looking at things with great rigor and depth, which give you a lot of insight and impact. And today's speaker, Professor Eric Michielssen, has a very similar impact in the sub-area of computational electromagnetics. And he received his PhD from the University of Illinois in 1992, where he then became a faculty member, became a full professor there in 2002. Then he shifted allegiance and also Big Ten football teams when he moved to Michigan. And he's been there since 2005, where he's now a professor, as well as he heads the computational science certificate there. He's got a long list of awards and many papers, more than 500 papers, journal and conference papers, long list of awards, starting with NSF Career and the URSI, which is the International Union of Radio Scientists fellowships, starting with the Young Scientist Award, going on to the Booker Fellowship, and then most prestigious, the Koga Medal from the URSI community. He's also got a lot of awards from Illinois and Michigan, including the Beckman Fellowship, the Sackler Fellowship from Tel Aviv University, the Sony Award, and many others. Now, what you won't see necessarily in his CV are two things I want to point out, is that he brings to this community a very interdisciplinary field approach, which is he looks at this from really 4 different aspects, these problems which he's going to talk about. He brings a lot of physics and physical intuition, really deep applied math, computational science algorithms, and then really deep engineering applications. So it really brings all these things to the fore together, and you'll see some of that. For example, you might see features of very different areas like compressive sensing or low-rank schemes and so on, and also flavors of some very famous algorithms such as the fast multipole method, which is one of the 10 best-known algorithms in this century from Leslie Greengard and Vladimir Rocklin, both of whom count Eric Michielssen as a very valued colleague and collaborator. He also has a great track record in terms of converting his students to academia. So I think out of his first 17 students, 12 have ended up in top universities in the United States. So that's a very enviable record. I have the pleasure and the challenge of being his first PhD student. I won't go more into that, apart from saying that after that experience, being chair is very easy. Okay. But it's been a wonderful experience. So let's give a hand to our today's speaker, Eric Michielssen.
Thank you very much, Vikram. Thank you for the kind introduction. I would say excessively kind introduction. It's really my pleasure to be here. University of Washington is a long-standing powerhouse in the field of electromagnetics. It's very nice to meet old friends and colleagues and students. And of course, mostly it's an honor to deliver this lecture named after a giant in the field, Professor Ishimaru. What I would like to do today is give you a bird's eye overview of some of the work that my students and I have been involved in over the past 7 to 10 years. My review, so in essence, I'm going to talk about work that we've done at Illinois and at Michigan on the development of fast and accurate time domain Maxwell solvers. Okay. My review is going to be partially historical in nature, but as my title implies, I will also talk about current efforts, and if time permits, I will also guess as to where the field as a whole is heading. Okay? Computational electromagnetics, and at this point, I'm not singling out time domain computational EM. It really has come a long way in the past decade. It's really a branch of science that I can say has come of age. When I was a PhD student myself, in the early 90s, we were focused on analyzing scattering from 2-dimensional objects. Okay, the gap between what we could analyze and what people in industry were interested in analyzing seemed like unsurmountable. Okay, so that has changed tremendously. This day and age, the gap between what people really want to analyze in industry and what we can offer, okay, as computational EMers, has shrunk. Has shrunk to the point that at this point, many in industry run even commercial CM tools on a daily basis. These things are part of the design cycle. It's really quite remarkable. So now what I would like to do today is give you kind of an overview or a feel for what kind of developments took place that enabled this, this transformation, if you wish. In essence, I'm going to talk about developments that allow, again, that once again allow engineers to run CEM solvers on a daily basis on fairly complicated geometries. Okay. Yes, I'm going to make I'm going to describe these developments from my own viewpoint. Okay, from the perspective of a developer of transient electromagnetic simulation tools. But many of the remarks that I'm going to make, they really apply across the board, also to other environments such as static solvers and time harmonic solvers. So in the early 90s, when I entered the field, the main problem that we were interested in, okay, at that time was scattering from aircraft, stealth aircraft and things like that. In the mid-90s, late 90s, we kind of moved on to problems involving wireless propagation. Since I moved to Michigan, of course, with the car industry being so nearby, I've gotten more involved in analyzing antennas mounted on vehicles, cars. And then more recently, even more recently, I've gotten involved in bio-EM interactions and interactions of EM waves on chips and things like that. But the technology that I'm going to describe is really fairly generic, okay? It kind of applies across the board to all these different structures. So ideally, if you're an EM engineer, okay, if you're in industry and you're asked to design, say, a cell phone, okay, or an antenna that mounts on a vehicle, what do you need? Well, you need a solver that can find ENH fields throughout space in an environment that is occupied by complex objects that involve perfectly conducting structures, perhaps with wire attachments, perhaps structures which are coated. These conducting structures, they may reside next to dielectrics, which may be homogeneous or inhomogeneous. There also may be magnetic material involved. I'm getting more and more into micromagnetics too, so this is important. And then you want to, assuming that you know how this thing is being excited, you want to figure out what the currents are on these objects and what the fields are scattered away from the objects, right? Okay. So and what are you really worried about? Well, you're worried about computational efficiency and speed. An engineer in industry typically wants to wait for about 5 or 10 minutes, or at most an hour, before seeing results appear on his or her screen. On top of that, of course, you're very worried about accuracy. How reliable are these numbers that the computer spits out? So I'm going to describe to you now in the next 40 minutes some key developments that took place in the past 10 years that have increased the computational speed of existing solvers by orders of magnitude, and also influenced their accuracy, especially when dealing with multi-scale geometries, to the point that most of the time the results can be trusted. Okay. Okay. So this short introduction aside, I've kind of decided to break my talk into 3 parts. It is impossible for me to introduce this topic to you without showing you equations. It's just not possible. I'm sorry. So I'm going to start out my talk with a section entitled Time Domain Integral Equations for Electromagnetics 101. Okay, so it's going to be a very basic introduction to time domain integral equations. All right, and then I'm going to talk about what I believe to be the 2 most important components of these solvers that have allowed this transformation, which have allowed engineers in industry to apply on a daily basis CEM solvers to design. Okay, and then if time permits, I'll make some predictions as to where, again, I think the field is heading in the future. Okay, time domain integral equations 101. Here we go. So suppose that I want to analyze transient scattering from an aircraft or sphere. Okay, to keep it simple. Many of you may do this by making use of commercial packages such as the German software, the CST software, or other finite element or finite difference based tools. The methods that I'm using are slightly different. Okay, the methods that I'm going to talk about today are not finite element or finite difference based. No, they're integral equation based. Okay, so what I do if I want to figure out what kind of time domain field is scattered by an object like that when illuminated by some external pulse is I'm going to go after the currents, the time domain currents, the transient currents that are excited on this object. Okay, so and I'm going to go after these currents by enforcing the fundamental boundary condition on the electric field that exists on the surface of these objects, which for now I'm assuming to be perfectly conducting. All right. So what is the fundamental boundary condition? Well, it's simple. The instant field, or better, the component tangential to the surface of the instant field must, of course, cancel the component tangential to the surface of the field scattered by the current J. J, that is the current excited on the surface of the object. That is the current that I would like to solve for. Okay? Okay, well, tau of J. So tau J gives you the field scattered by the current. Well, it really consists of two components. For the electromagnetic experts amongst you, it consists of a first component, which here I label tau S. Okay, that is really the vector potential component. That is the vector potential due to the current J, and then tau H. That is really nothing but the scalar potential due to the scalar potential contribution to the field produced by the transient current J. Okay, the S here stands for singular. The H here stands for hypersingular. I'll come back to that later. Okay, so okay, plug these expressions into the one there on the first line, and you realize that we have a time domain integral equation for the current. If I can solve it, well, then I'm in good shape, and then I can figure out the field scattered from the object and so on. Okay, so how do we go about solving that equation? Well, it's pretty simple. You mesh the object. In practice, you approximate it by a number of triangles, and then you approximate the current on those triangles in terms of a finite basis. Okay, so since I work in time domain, the basis has two components: a spatial component and a temporal component. Okay, but multiplying all these known functions are these coefficients here. Okay, these are the so-called expansion coefficients. These coefficients here, they determine the magnitude, the amplitude, if you wish, of the current as a function of time. So there are two indices here, okay, and that is because, well, the current varies as a function of space. That is the n here. It also varies as a function of time. That is the j here. All right? Okay, so you plug that expansion for the current into the time domain integral equation, and then you somehow test it. I'm not going to explain you how exactly you go about testing it, but as an end product of this testing procedure, you come up with this huge matrix equation. Okay, and I think I can explain you where this thing comes from and what it means. Okay, the first equation that you see there, that is the equation that you enforce that determines the currents at time step 1. Okay, look at the equation on the first row. It says Z0 times I1 is equal to V1. So what does this mean? So prior to time step 1, there are no currents on the object. Okay, everything is quiet. An instant field hits the object. It creates an electric field on the object. That electric field is measured by this vector V1. And Z0 times I1, that is the field produced by the current at time step 1. It must cancel V1. This gives us the current. By solving the equation Z0 times I1, I get the current at time step 1 in the analysis. Okay. Now, let's now move on to the next time step. The field at time step 2, it consists of two contributions. It consists of the contribution of the currents active at time step 2, that is Z0 times I2. It also consists of the field produced by the currents at time step 1. By now, these fields are flying through space at the speed of light, but they do affect the field on the object. But of course, I know the currents at time step 1 already. I've solved for those at the previous time, so I can move those to the right-hand side. And so this means that at time step 2, I can solve the second line in that equation. Okay, Z0 times I2 is equal to V2, the incident field at time step 2, minus the field that is produced at currents which were active prior to time step 2. You see? And so on and so on. At each and every time step, I can solve for a new spatial snapshot of the currents on the object. Once I know the currents at a given point in time, I can move them to the right-hand side, and I can march on in time. I can do MOT and find the currents at the next point in time. See? That's how this thing works. So it's somewhat similar to say, the FDTD, fine difference time domain, or fine element time domain solvers that some of you may be familiar with. It's different in the sense that we don't solve for fields around the object. No, I solve for currents on the object. Okay? And these currents, they propagate through space at the speed of light, characterized by Green's functions. That's it. All right. Okay, these equations here, I can also write them in this form here. This form of the equation will appear throughout the talk. It's really the same thing. This is one row of this equation here, a generic row. At time step j, you make sure that the field produced by the current at time step j, that is that thing there, plus, if you wish, plus the field produced by all the prior currents. You make sure that total field cancels the incident field, Vj. Get it? That's it. All right, good. So this all looks nice, right? Well, there are problems. There are huge problems. This kind of methodology was known to engineers and mathematicians back in the 60s and 70s. Yet it was never used. It was never used for good reasons. I'll skip this slide. For good reasons. See, how do you go about solving this thing? Let's go in perhaps in even a bit more detail here. If I want to solve for the current at time step j, the first thing I have to do is compute the right-hand side. Okay? Well, presumably, of course, you know your instant field. So computing Vj, that's easy. But you also have to compute that sum. And again, what does that sum represent? It represents the fields that hit the object at time step j, which are produced by currents which were active prior to time step j. So again, these are fields which have been propagating through space at the speed of light, produced by currents which are active in the past. All right. Well, computing those is expensive. You can easily show that if I approximate my airplane or my sphere or whatever by ns, and here s stands for spatial, by ns triangles, then the cost of computing that convolution, because it's a convolution, will scale quadratically in the number of spatial points. And that is really because we use the Green's function approach, and also on all points on the triangle on the surface interact with all other points on the surface. So computing that convolution is extremely expensive. Extremely expensive. About 10 years ago now, my students and I, we developed this plane wave time domain scheme. More about it soon. It is a scheme that allows you to compute that ugly sum, not with a cost that scales proportional to the square of the number of spatial basis functions. No, it allows you to compute that sum at the cost that, in essence, give or take some logarithmic factors, scales linearly in the number of spatial basis functions. Okay, we've come up with a number of ways of doing this thing fast now, but this PWD scheme, this plane wave time domain scheme, is our main workhorse till this very day. More about it soon. Okay. Now, secondly, suppose that you have computed all these things rapidly. Suppose that you have computed the right-hand side rapidly. Now you still have to compute. Now you still have to solve the matrix equation on the left-hand side. Okay. Turns out that is also problematic. It is problematic because we typically don't solve these things directly, say using LU decompositions or things like that. No, we solve them iteratively. And it turns out that this matrix equation is often ill-conditioned. By this we mean that the ratio between the largest single value and smallest single value is very large. And this means that if you solve this thing iteratively, by first making a guess for ij and then correcting it by multiplying over and over that matrix by trial vectors ij, turns out that procedure converges extremely slowly. Extremely slowly, especially when the geometry that you're analyzing has many small multi-scale features and things like that, which is, of course, exactly what engineers these days are interested in. Okay, well, to address that problem, we developed a whole bunch of preconditioners, including time domain Calderon preconditioners, in essence extending lots of the work that Ben Denbart did early on in this field to time domain. And so now we're kind of in business, okay? We can very rapidly compute all the components of this equation. We can very rapidly compute the right-hand side. We can very rapidly solve that equation because we have very, very good preconditioners. Okay? So now I'm going to tell you a little bit more about these two ingredients here, which make up modern time domain solvers. Okay, so I'm going to say a few more words about this fast multiple method without going into any technical details, you know, and about these Calderon preconditioning methods that we developed. Okay, so again, what do fast multiple methods do, or what does our plane wave time domain method do? It accelerates this sum here, right? It accelerates this sum here. Okay. Okay. If you think about it for a little while, you realize that sum is nothing but a discrete expression of an integral of this form here. Okay, of this form here. If you have a surface, and if on that surface you define sources sigma, if you can very rapidly compute this acoustic field, if you wish, this scalar acoustic field from these sources, if you can do this rapidly, then trust me, you can also very rapidly compute the matrix vector products and the convolutions which appeared on the previous slide. They're one and the same thing. So, can we very rapidly compute integral transforms like that? And if you're not interested in doing time domain analysis, okay, if you're interested in doing time harmonic analysis, can you very rapidly compute integral transforms like that? Or if you're doing static analysis, if you're interested in computing capacitances of chips and things like that, can you very rapidly compute transforms like that? Well, yeah. Turns out that typically the cost of doing this scales quadratically in the number of points on the surface. But if you make use of these fast multiple methods, you can once again reduce that cost to something that scales roughly linearly in the number of points on the surface. So here's a little chart that shows how these things and when these things were developed. The earliest fast multiple methods, they date back to the mid-80s already, so they're already 20 years old. Fast multiple methods for doing time harmonic analysis, well, that all dates back to the early 90s. And then again, this plane of time domain scheme, which I just alluded to, that accelerates the solution of time domain integral equations. Well, the development of that thing scale dates back to the late 90s. Okay. Okay. Now you see. Now you may say, okay, Eric, all this is already 10 years old, 12 years old. Why do you still talk about it? Okay. Why do you still talk about it? Move on. Well. As Vikram said earlier, these schemes were selected by the IEEE Computational Science and Engineering magazine in the year 2000 as one of the top 10 algorithms of the previous century. So again, why am I still talking about it? Well, I'm still talking about it because these methods are not only still in vogue. Okay, there is still very active research ongoing on these methods. If you attend an IEEE antenna and propagation meeting, you see that every year there are still many sessions, 5, 6 sessions on fast methods for computational EM, and just about all papers in these sessions, they focus on the development on further developments of fast multiple methods. Nick Trefetten, now an applied mathematician at I think it's Oxford or Cambridge, I always forget. He in the mid-90s wrote this little opinion paper, which I think you can still find on his website, and it contains 10 predictions for scientific computing. Okay, and I'm going to let you read this by yourself. In essence, prediction number 7 deals with fast multiple methods. He predicts that fast multiple methods will influence, in essence, all branches of computational science and engineering, and moreover, he predicts further on in his paper that they will continue to be an active field of research well beyond 2010. He says this specifically, and that's exactly what we're observing today. Last year, the Gordon Bell Prize was, which is probably the most coveted prize in parallel computing, okay? It was awarded to a team headed by Dennis Zorin and George Biros from Courant, and, well, George moves around. I think now he's at Austin. Okay. They analyzed, so this is not a CEM, it's not a computational EM application, okay? They analyzed, using fast multiple methods, the flow of blood cells, okay? It's just unbelievable what they pulled off. By making use of fast multiple methods, they were able to analyze the flow of 200 million blood cells. It's unbelievable. This translated into 90 billion unknowns. So effectively, they were solving dense matrix equations 90 billion by 90 billion. Just unreal. Okay, and of course, they need the big computer for it. They use about 200,000 processors. But so what? They did it. Okay. In computational EM, we're not there yet. Okay, this is a fairly simple fast multiple method. It's a static kernel. In computational EM, when we talk about high frequency phenomena, time harmonic, we're roughly at 1 billion. If we talk about transients, we're roughly at 50 million. Okay, but that's roughly where we are. So far removed from 90 billion. Yet, if you look at potential engineering applications, there are many out there that call for a few billion unknowns. Okay, roughly 10 billion is kind of where the sweet spot is. So more work needs to be done. Okay. Okay, so here you see a few other applications of this technology. Using time harmonic fast multiple methods, it's now possible to analyze complete optical systems without doing any ray tracing. Okay, you can do an ab initio analysis of complete lens systems and very, very, very large photonic crystals involving tens of millions of unknowns. Okay, and all this can be done in about an hour on a fairly small parallel computer. It's interesting. Okay, how do these things work? Well, again, I'm not going to go into any details here, but for those of you who have never been exposed to this, let me just say that these are hierarchical algorithms that start from a geometry. Here again, I assume that the geometry is a sphere or a circle, and that hierarchically break this structure into substructures, and then they don't evaluate the fields produced by currents here, over there, by looking at point-wise interactions. No, these methods, they make use of so-called plane wave expansions in order to collectively, in order to evaluate the collective fields of sources over here, say over there. Okay, so in a complicated way, they take this original matrix Z, or that combination of matrices Zi that encode fields produced by individual sources, and they decompose them into a product of many, many matrices that each of which is very, very sparse, and which in the end produce the same matrix. That's fundamentally what it is. So if in a classical computation of the fields at all these points here, due to all these sources here, if in a classical computation all the points and observers interact directly, in a fast multiple method, this is not the case. In a fast multiple method, they interact with each other indirectly through the plane wave spectra of groups of sources. Simply the fact that there are fewer lines in this picture than in this picture means that there is a way, or implies that there is a way, to reduce the computational burden, and that's exactly what fast multiple methods make use of. In a multi-level framework, you can reduce the total cost from something that scales quadratically in number of unknowns to something that scales linearly in number of unknowns. Okay? Let me show you some examples. This here is a ship. You know, again, in tiny we go up to 10 million, 20 million, 30 million unknowns. Yeah. This ship is not that big. It's about 140 wavelengths long. Okay, and I have an antenna active right there. Okay. And it radiates a field, and the field produced by that antenna is picked up by an observer which sits somewhere else on the surface. Okay. One big advantage of these tiny integral equation methods, or in general of integral equation methods over differential equation methods, is that they're very, very accurate. So the dynamic range in our computation here is substantial. Often we get 4 or 5 digits in essence automatically. Okay. So here the field that is picked up, or the current that is picked up by the receiver antenna, which sits somewhere on the back there, is very, very small. Okay, a fraction of a milliamp. Again, to compute these things with that kind of accuracy, well, you would have a hard time doing it with finite difference solvers. With integral equation solvers, it's fairly easy. We have embedded these solvers in multiphysics, multi-domain frameworks, which allow us to do fairly complicated things, such as the analysis of electromagnetic compatibility and interference phenomena. I'm going to show you a few examples here. So in this framework here, the CEM solver, which I just described, it interacts with SPI solvers, with cable solvers, and so on, in order to analyze even more complex phenomena. So again, since I moved to Michigan, I've been working on cars. Okay, so here we have a very old Camaro, and it's loaded with cables, and there's electronics in the back. You see, and there are a whole bunch of antennas active. And so the question is, if you operate these antennas, in this case these are GPS antennas, when you operate them, they create signals which may leak into the cables, and which may then in turn, of course, upset the electronics. Okay. So there we go. So we activate some of the GPS antennas which are on the mirrors, and then the signal goes through the windshield, which of course we model. Yeah, our solvers of course are not limited to just perfectly conducting objects. Okay, we can also handle dielectrics and impedance surfaces and things like that. The signal moves inside, and then it penetrates through these cable shields, and then it propagates along the cable, and in the end seeps into the electronics box. So again, you need a very, very high dynamic range. Your solver has to be extremely accurate to detect voltages in the box here of, say, 10⁻³ volts. Okay, if the signal on the antenna is 10 volts, you need 4 digits of accuracy. Okay. Because we operate in time domain, we can of course also directly analyze nonlinear phenomena. So here we have a military vehicle. There is a receiver antenna there on the roof, okay, and attached to that receiver antenna is a nonlinear demodulator circuit. Okay, so in this case, the Humvee is illuminated by a plane wave, which is causing a signal in that receiver. But at the same time, there is also an aggressor active here. Okay, and it will also generate signals in that demodulator circuit. Well, this is an ideal framework for analyzing these things. Using these methods, we can analyze the impact of resonances of the vehicle on the blue line, which is the signal demodulated by the nonlinear circuit, and we can also analyze the effect of the aggressor on the received signal. You see, all in one shot. This one is always popular, so I'm showing it. So this is here we analyze the effect of using your cell phone on an aircraft. Okay, it's kind of the same problem as that original car I showed you. So here we have someone using a cell phone right there. It's going to light up in a second. There it is. And okay, that signal will again leak into the cables which run around the aircraft. And then in the end, they will end up in electronics that sits in the back of the aircraft here. Okay. Again, the signal that ends up here is very small. It's just a fraction of a millivolt. So the question is, will this mess up the airplane controls? I'm not going to answer that question, but in order to calculate this, again, you need very, very accurate solvers, and we supply those now. Okay, now here's one problem. Many of these structures, okay, they contain, I'm not showing them here, but they contain very, very small geometric details, very small, fine features. So for example, in this box here, there can be a card, okay, a computer board. And on that computer board, you can have small traces, okay, and lumped components. All right. Well, if we model all these very, very small details directly in our solver, something happens. What happens? Well, I alluded to it before. When we solve this equation here for every time step, the solution of this system of equations slows down. It's just your iterative solver tends to grind to a halt. So these fast multimeters, which I alluded to earlier, which I described just a minute ago, they allow you to compute this thing very accurate, very, very rapidly. But you still have a problem now. When your structure includes very small, very fine geometric details, the solution of this system of equations becomes problematic. It just slows down. I'm not going to go into much detail here, but the problems associated with this slow convergence, they can be traced to the so-called spectral properties of the operators involved in that time domain integral equation. Again, there is a singular component to the operator, that's the vector potential in engineering language, and there's a hypersingular component, that's the scalar potential contribution in engineering language. These two operators have vastly different spectral properties, and those spectral properties, or those differences in spectral properties, they result in this matrix having a very, very high condition number if the mesh density goes to 0. And of course, everybody these days is interested in multiscale analysis. Okay, we're no longer interested in analyzing, say, scattering from a very large, smooth aircraft. No, we want to load that aircraft with very small antennas. We're no longer interested in analyzing a very simple and uniformly meshed bus for a chip. No, we want to attach to that bus vias and nonlinear components and things like that. We are interested in fine geometric details and their impact on the functionality of components. And so the ill conditioning of this matrix is more the norm than the exception. It's something that we have to deal with. Well, it can be dealt with. Okay, and this is a fairly recent breakthrough in time domain. It can be dealt with by not just enforcing the fact that the electric fields produced by the current cancel the instant field. No, it can be dealt with by reworking the equation in this form here. Okay, so what does this equation here tell you? Again, tau of J is the electric field produced by the current. Our previous equation said that electric field produced by the current must cancel the instant field, or the tangential component thereof. Now I'm writing down here a new equation. It says that the electric field of the current must cancel the electric field produced by, well, sources which we can think of as the instant field. It's very strange. It's very, very strange. Well, the equation, of course, is easily derived. It's easily derived because you just take the original equation that I have, and now you compute the electric fields of both left and right-hand side again. It's easy to derive, but why? Why is this a better equation? Why is this equation good for analyzing structures with very fine geometric features? It's unclear. I'll tell you, engineers would never have written this equation down. Okay, and this is kind of a message that I would like to get across. For further progress in this area to be realized, engineers will have to become better mathematicians. Okay. Turns out that this equation does not suffer from these spectral properties that the original time domain equation suffers from. If you discretize this equation, if you put it in this marching on in time format, where you solve for a snapshot of the current, one after another, turns out that the matrix that you get, that the matrix equation that you get, has diagonal terms which are well conditioned. They are well conditioned irrespective of the strangeness, if you wish, of the mesh. Even if you have very, very small geometric details in the mesh, the matrix behaves just fine. And the solver will converge in a very small in a very small number of iterations. So this is crucial for the EM engineer. Okay? Without this kind of development, if you use this kind of solver, you run into trouble sooner than later. With this thing in place, you're in business. Again, a lot of the early work on this kind of technology in the frequency domain was done by Ben Dembart and his group. We've now been able to do all this in time domain, and moreover, we've been able to do it, which we can talk later on, in a so-called multiplicative way, in a way that does not force us to decompose operators and things like that. It's quite different from what you've done. Yeah. But here are some examples. So here you take a sphere. Okay, who's interested in a sphere? Well, let's see how our algorithm acts on a sphere. So you take a sphere, okay, and you analyze scattering from that sphere, a tiny domain scattering. You then refine the sphere. You make the mesh denser and denser and denser. Okay, so here on this axis here, I show the edge length, the maximum edge length of the mesh. So if I move from here to here, then the edge length will shrink. Okay, if I don't use this special solver, this Calderon preconditioned solver, which we just developed 2 years ago, then the cost per time step, as the mesh shrinks, goes up. That's the blue line. It goes up. It goes through the roof. But with these new preconditioners in place, it stays flat. Irrespective the density of the mesh, the solver converges rapidly. Okay? So there are incredible implications for this. Here's a space shuttle. Okay? We have a very crude mesh everywhere here, except for that's kind of sad. I think I'm missing a slide. There is this may be it here. There's a slot antenna right here. Very densely meshed waveguide slot. Okay. The density of the mesh here is so high that perhaps it's given there. No. Here we go. The density of the mesh there is so high that without Calderon preconditioner, the solver will simply not converge at all. You see, the density of the mesh is such that you can't even see triangles there. See, previously, in the olden days, engineers would be very reluctant to properly mesh an object like that, because they know that the solver would not converge. Now, this day and age, we don't care about it anymore. We just sprinkle in more and more points, more and more triangles, in order to better approximate the true geometry of the object. We're no longer afraid of our solvers stalling. They will converge. So you see here that the number of iterations of this thing without preconditioner is 6,000. Okay, it's huge. With preconditioner, it's still 200, but it's much better. Here's another example. Here we have an antenna. It's a probe that sticks into a waveguide. Okay. Here's the probe. Here's a detail of the probe. This is the coax. This is this region here. Okay. In the past, engineers would have been very reluctant to discretize this wire, this probe here, with the number of unknowns required to properly describe all the currents and fields here. This day and age, we don't worry about it anymore. We just sprinkle in additional points, whatever it takes, in order to properly describe that geometry. The solver will converge rapidly. So here we go. This graph here shows you what we call the residual error, the error in the matrix equation as a function of number of iterations. Okay, for the non-preconditioned solver and the preconditioned solver. The non-preconditioned solver, for this, when this very fine mesh is present, takes a long time to converge. The preconditioned solver is converged extremely fast. This is no longer affected by the density of the mesh. Here's same theme, you know. Here we have a truly multi-scale structure. I have a big dish antenna, and then next to that dish antenna, there is, well, look at it. There's a monopole. Okay, so zoom in and zoom in again. The mesh near the monopole is very fine compared to the mesh on the rest of the structure, on the pedestal and on the dish. Without preconditioner, look at the upper graph there. The solver, the residual error in the solver, as a function of iteration count, it just does not converge. But with the Calderon preconditioner in place, it just takes 20 or 30 iterations for this thing to converge. in time domain. Just more the same. Metamaterials. So now we can analyze metamaterials much faster than we could before. Okay. All these things are very, very small compared to wavelength. There are gaps here, split ring resonators, which have very, very tiny gaps here, which call for very, very fine meshes. Without Calderon preconditioner, it takes forever to converge. With these things in place, you don't worry about it, kinda. And here's the last one I want to show. This is a complete computer board. I only show one side, but there are multiple sides to this. And there are vias going through, and there are drivers, active drivers and things like that connected to all these pins here. And also right there, that's where the CPU sits, under the big heatsink. Okay? So this geometry is truly multi-scale in nature. The size of the smallest edge to the longest edge is like 1,000 here, or even 10,000, I forgot. Without these fast multiple accelerated and Calderon preconditioned solvers, there is no hope. You just cannot analyze this. With these techniques in place, we can analyze this complete board. In this case, this was done for, well, I'm not sure I'm supposed to tell you. But the board did not function properly, and we were able to figure out, using our solver, where exactly the error occurred, where the signal jumped from one trace to another trace. Okay? And again, I'm only showing one side of the board here. There are multiple sides, and there are active components involved and things like that. Okay? I also should mention, of course, that we just don't model the perfectly conducting traces here on the ground planes. No, we also model all the plastic, all the dielectric. Everything is being modeled faithfully. This involved roughly 1 million unknowns, spatial unknowns. So it's really not that big a problem. All right. Conclusions and some predictions. So I hope I've kind of convinced you of the fact that again, CM has come a long way. We now have fairly competent, mature solvers that can tackle a wide variety of problems in a robust fashion. Okay? How do we get this far? Well, for sure, it was Moore's law, and the realization that in order to speed up solvers, you didn't have to go after leading constants in cost equations. No, you went after the exponents. Okay? The guys who originally developed the fast multiple method, I mentioned them before, Vladimir Rocklin and Leslie Greengard, they they immediately realized that it was the order n square, the square in that equation, scaling that prevented these methods from being applied to large-scale problems. So they reduced the exponent, and by doing so, they made these into practical tools. Perhaps associated with that, there's also, how should I put it, a change in mindset amongst applied mathematicians that took place a long time ago, or 40 years ago. The mantra was, or the prevailing thought amongst mathematicians and applied mathematicians was that the purpose of computing, okay, is insight, not numbers. Okay, people were not going after highly accurate solvers. This day and age, no more. Leslie Greengard is well known to have said the purpose of computing is numbers, okay, and specifically correct numbers. So these days we go after digits. We want the answer. If I give you a board, or if you give me a board, I will tell you that the voltage on this board at this pin is 1.065543 volts. Okay, exactly. And this then allows you to play other games. Okay, now so we've come a long way, but are we done? No. Okay, we simply cannot rest on our laurels. It's too early for that. Just last week, I asked one of my students to analyze a fairly simple, microstrip patch antenna. It was a circularly polarized single-feed microstrip patch antenna. I asked him to run two solvers, a FICO solver and an IE3D solver. Both are integral equation-based solvers. Okay, and I asked him to plot for me the reflection coefficient as a function of frequency. Okay, that's the graph. These are the graphs he got. Okay, yeah, there is some agreement between the results produced by these two solvers, but the agreement is by no means great, right? So there are several reasons for that. One reason is that these commercial solvers do not yet have built in all the advances made in academia. Okay, so many of the things that I talked about here, the Calderon preconditions and things like that, they're not yet in these solvers, as far as I know. Okay, and this causes some of these problems. But there are other culprits. Okay, there are other issues that remain to be resolved for these discrepancies to disappear. Okay, and they relate to treatment of field singularities, treatment of high contrast interfaces and things like that. When it comes to fast multiple methods, incredible progress can still be made in parallel implementations. Okay, I previously told you that George Biros and Dennis Zorin were able to analyze 200 million blood cells on 200,000 processors. Again, something like that has not yet been realized for electromagnetics. Okay, so as it stands, even fast multiple accelerated and preconditioned integral equation solvers, they remain too slow and too inaccurate, for example, for doing closed loop design. And they remain too slow, especially for doing high dimensional uncertainty quantification. These days, people are very interested in what ifs, in exploring what if scenarios. So suppose I have a patch antenna. Okay, what happens if I change the dimension of that patch slightly? What changes if I change the loads attached to the patch slightly? Very often people are interested these days in modifying, in seeing the effect on output variables, on observables of changes in not 2 input parameters, but in say 100 or 1,000 parameters. Okay, well, there exist techniques out there for addressing that problem, but all these techniques call for a solver to be run inside the loop, and our solvers at this point are too slow. Even though they're fast multiple accelerated and well preconditioned, they're too slow. So, then where's the field heading? Okay. Well, I did allude to this before. We're going to see in the future new and even faster and even better conditioned integral equations pop up. Okay, but their development will require a tighter connection between the development of these solvers and mathematics. The development of these new solvers will require more mathematics or more mathematical input than we've seen before. We've seen some evidence of that already. Okay, when I talked about these Calderon preconditioned solvers, these are solvers which are non-intuitive from a physical perspective. An engineer would not have written them down, but a mathematician would, because a mathematician understands the impact of the spectral properties of the operators on the convergence, for example. There are additional, there is additional evidence, that this is happening already. Fairly recently, Leslie Greengard, whose name I brought up in the context of the development of the original fast multiple method, together with Charlie Epstein from the University of Pennsylvania, they developed a whole new type of integral equation for analyzing scattering from perfectly conducting objects. An integral equation that engineers previously had never written down. Okay, and it's actually a very nice equation. It's one that has incredible properties in terms of low frequency stability, dense mesh stability, and stability in the resonance regime. It's a magical equation that somehow had escaped all engineers. Mathematicians found it. So, well, engineers should sharpen their math skills. That's what I'm saying. Another development that for sure is going to take place, okay, is implementation of fast multiple methods on GPUs. This also is already starting, okay? And quite frankly, I'll admit to you, okay, I kind of missed the boat here. I thought that this was not going to be important, but it turns out it is. the group at Courant and Georgia Tech would not have been able to analyze 200 million blood cells using 90 billion unknowns were it not for GPUs. In order to port an algorithm to a GPU, especially high-frequency electromagnetic fast multiple kernels, the entire algorithm must be rethought. It must be the layout of data and things like that on a GPU is vastly different from that on a CPU, and so a lot of work will go into converting our algorithms to GPU format, if you wish. Okay. Is this good science or not? I don't know, but it's going to take a while, and it will happen. Okay. Then there are other things here. Okay. Randomization. Okay. All the schemes that I described to you up to now, they are deterministic in nature. That is that, and by this I mean the following: for a given input, they produce a fixed output. They internally do not rely on any, say, random number generators, right, to produce output. No. They're deterministic in nature. You may even think of it as very strange that I bring up the notion of randomization in a deterministic solver framework. But there is evidence that future CM tools will internally make use of randomized schemes. Randomized schemes are popping up all over the numerical linear algebra world. You know, you can compute the single value decomposition of a matrix using classical schemes. In MATLAB, for example, you can use you can say SVD of a matrix, and it will compute the SVD of a matrix using a deterministic scheme. But recently, new schemes that make use of random projections have been developed that outperform all the deterministic schemes in both accuracy and speed. Okay, these things were developed by Vladimir Rocklin and some of his students, and also elsewhere in the country. You know, well, there's now already evidence that many of these randomized schemes that they likely will lead to fast direct solvers for computational EM, and I don't, and I'm pretty sure that at some point we will also see randomized fast multiple schemes, okay, which will outperform existing deterministic ones by an order of magnitude in both speed and memory consumption. And then last but not least, sparsification. So everybody here, of course, has heard about all the L1 buzz and compressed sensing and things like that. There is no doubt in my mind that not too long from now, many of these ideas will make it into computational EM tools. We have recently, and I don't have enough time to show this to you here, we have recently demonstrated, I think, the first rigorous high-frequency time domain integral equation solver, a solver that seamlessly transitions from low frequencies, where you describe the fields mostly in terms of currents on objects, to high frequencies where you describe fields in terms of rays. And that was achieved by exploiting sparsity, natural sparsity that occurs in plane wave representations of transient fields. The solver that we developed did not leverage any L1 or compressed sensing notions, but those are not too far around the corner. Trust me, this is all going to happen. And when this happens, okay, and this is now my last slide, I'm going to make a bold and pompous claim, okay. Before I retire, I will have to switch research fields. I give it another 10 years. And I think 10 years from now, okay, we will have Maxwell equation solvers that given a deterministic input, for example, a computer board, okay, with tons of vias and loads attached to these vias and things like that. We will have Maxwell equation solvers that, given a deterministic input, will produce output, say voltage sources at pins and things like that, to, in essence, arbitrary accuracy, irrespective the multi-scale nature of that object, irrespective of the materials that it's made of, and things like that. Why do I say this? I say this because I think that most of the components to realize a solver like this have been developed, or they're in the works, or I kind of see where they will come from. I'm pretty confident. So yeah, I'll come back 10 years from now and we'll see. Okay? Thank you.
We have time for a few questions.
What about dynamic range? So you showed about 80 dB or so dynamic range.
Yes, so I
have problems that I would love more. What do you see in the future for dynamic range?
So I did not talk about our work on high-order solvers, but a lot of these Calderon solvers recently have been made high-order in nature, and so with those solvers, I don't know. When we do circuits, we don't. When we do low-frequency application, we don't typically think in terms of dB. You know, 6, 7 digits is possible. Leslie Greengard claims to have a solver now that does 10 digits, 3D. For some reason, I cannot deliver that, but we're at 6 or 7 digits routinely. Jim Bremer from Santa Barbara, I think, recently developed a bunch of quadrature rules that apparently are key to going to 9 or 10 digits. Yeah. So yeah, this is all possible.
You mentioned non-linear problem, but how about dispersing material?
Yes. So I did not talk about this here, but we've published a number of papers where we apply these time domain integral equation solvers to fully dispersive and lossy materials. Of course, okay, there's a caveat here. We always assume that the response function has a simple description. Okay, a few poles and things like that. If that is not the case, well, then you have to bite the bullet and do the full convolution. And there exists at this point. That's actually good. You bring up an important point. At this point, there exists no fast ways for doing the convolution if the response function of the material does not have a specific form. This is still an open question. Yeah.
Okay. I was just wondering if you care to predict 10 years from now, what fraction of the progress would you say will be computational speed and memory size as opposed to output?
Okay. Let's look back. Which fraction of the progress in the past 20 years was computational speed as opposed to algorithmic? You may think that computers have gotten a lot faster, okay? But no. The fraction of progress due to increasing computational speed are epsilon compared to progress due to improvements in algorithms. I can put some numbers on the board here, but it's overwhelming. The algorithmic progress is 9.9%, and I cannot predict the same thing will happen again. Although GPUs, they kind of may upset the apple cart. I don't know. Yes.
Curious about your time domain integral equation. If you want to analyze real low frequencies, very low frequencies, that sort of thing, do you need how long response times do you have to do that?
Okay. It's important to realize that when we determine our time step for these solvers, the time step is not determined by the edge length in the mesh, as it is when you do, say, a fine difference solver. These systems these solvers, they're implicit. The time step is dictated solely by the bandwidth of the impinging signal, if of course we're dealing with a linear system. So the number of time steps is simply determined by the duration of the pulse of the current on the object. The number of time steps does not go up if we go to very low frequencies. You see? I'm not sure that I fully answered the question. Okay.
Talk to you later.
Yeah.
Thank you, Professor, for your presentation. I have two quick questions. Is it troublesome for a user to model those multi-scale geometries in the software? And the second question is, can we use lumped models to simplify the problems?
Okay, so there are two questions here. The first one is it difficult for a user to model these multi-scale structures? Well, I don't know. I would say no. The whole point of developing these solvers is that we want to relieve the user, the mesher, from any concerns that he or she may have about the density of the mesh messing up the accuracy of the solver. Throw in sprinkling points. It's okay. You don't have to worry as a mesher about the impact of that mesh density on your accuracy. And also, this also works in the other way. Suppose that as a computational EM guy, you get a mesh from a different application, say from a mechanical tool mesher, okay? And suppose that this mesh comes to you, and suppose that the discretization is way too fine in a certain region, which is electromagnetically inactive. In the past, engineers would spend days and weeks and months electromagnetically defeaturing the mesh, taking out elements in order to avoid the breakdown in the solver. Now it's no longer needed. You just run the thing through. Your second question, can we model certain pieces of objects in terms of lumped elements? Yes, we do that, okay? So this chart was kind of meant to convey that. We have put together a fairly complicated framework. I'm not the only one who has done this. Vikram has done very similar work, where we interface all these solvers with SPICE solvers and cable solvers and reduced order modelers. Okay, so now of course, when you model something faithfully and when do you replace it by a lumped component, that's a judgment call.
Okay, we have time for one more question. Come on, this is your chance. One more.
I don't think we need the time.
Okay. All right, so I think we're out of time. So let's thank the speaker, Michielssen, once more.